derivative of my power.
Word on the street or suspect.
Okay, here we go. Here's where we left off yesterday. So click and close, let's have a quick look here. I mean, I guess you don't have to click and close if you don't want to.
Oh, I don't.
I would sort of encourage it. Test tomorrow. Calculate the derivative of the following function. So how would we, I mean, this really isn't that hard, but we gotta make sure we think about it correctly here. We gotta write this so we can see the layers. Right, what's the outside layer?
To the 1/2.
1/2 power, okay. And then inside that, we've got a 5 plus cotangent squared x, but what's cotangent squared x?
U squared times.
Okay, it's the cotangent x quantity squared, right? So, okay. So then if we wanted to do this, if that's y, what's y prime be? It's the outer derivative by the chain rule. 1/2 times tan to the
Negative.
okay. Good times. Now the derivative of the next part. Let's see the next part here. So I'm gonna have some people just think about it for a second first. I'm gonna call on it. Just randomly calling people. So the next layer, we got rid, and let's erase them as we go. I think this sometimes helps. What did we just do? Well, we erased the outside one, right? We took the derivative of the square root. Okay, so now what's gonna be next here? So Hannah, what's gonna be the derivative of the next layer? Derivative of 5 plus cotangent squared x. Derivative of 5 is? Yeah. 0, okay, good. And then what do I got here? What is this one again? Which layer am I differentiating here, the cotangent or the square? Square, okay. So what's the derivative of hand squared?
Cotangent.
2, okay, good, 2 hand to the 1. So we get times 2 hand to the 1. And what's the hand?
Cotangent.
Cotangent x, okay. So we got rid of, what did we get rid of there? That's gone with this derivative, and we got rid of the squared. Okay, and so Landon, what's next one? What's our next step?
Is that a cotangent?
What's the derivative of cotangent?
Secant.
Say it again.
Is it secant squared?
Derivative of cotangent is
So it's cos.
negative cosecant squared. There we go.
Are we able to use our sheet on the test?
No, you got no derivatives.
Oh.
Yeah, you got no derivatives.
I know how
In fact, I'll tell you what I'll even, yeah, you gotta learn them. You gotta learn them. I will, remind me to print out, did I give you the, I think I've given you the new one, but if I haven't, I'll print it out. It's on Moodle, but I'll print out the new one today so you can have the derivative sheet. And you know most of them, right?
Yeah.
But you do need to know these. I'm not, you know me, I'm not a big fan of memorizing stuff, except that when you're doing calculus, it breaks your train of thought if you can't remember the derivatives. You just gotta know them. Because then you can, you don't, you can just focus on the calculus and not think about remembering what those darn derivatives are. There aren't very many. There aren't very many that we're using. Yeah, you gotta know them. So there's our answer. We would just write it as a fraction then, right?
Is it just gonna be like sine, cosine, cotangent, secant, cosecant?
Mm-hmm.
And, okay.
And then we added, we've got e of x, we got natural log x, we added, that's it, right?
Okay.
Product rule, quotient rule, power rule.
Just for like the trigonomic functions.
Yeah, so you get the
just be
six, you got the
six
six,
basic.
6 trig functions, and then just the power rule, product rule, quotient rule, exponential, logarithmic, yep. Okay, what about this one then? I mean, this, we probably don't even need to do this. This is real similar, right? Just you tell me what's the outer layer here.
Cosine.
Cosine, you got cosine of hand, right? Next layer, sine of hand, next layer, 6e to the x, right? No big deal. We can probably skip that one. We'll come back to it if we need to. Okay, this one, why did I put this one up here? What's important about this derivative? What's important about that one? What should I do here? Brittany, what should I do to that one? Do I want to use quotient rule? I can, you're right, I can, it would work, but I don't really want to, I can do it more easily. Doing what?
With the fund.
Perfect, yeah, I'll use I'll use the general power rule, right, generalized power rule, and just make that a negative exponent. So all I gotta do here to make this easier is -6 times the quantity, 9x to the 4th plus 2 to the -5. No big deal now, right? Now it's just outer layer is the power, inner layer is the polynomial. So I got a 2-layer chain rule, power rule derivative there, no big deal, okay? Okay, what about this one? Okay, I put this up here because of the absolute values. I wanted to remind you of a point. Is that intimidating to see the derivative of the natural log of an absolute value? Why are they there? Why would we have absolute values of ours? Is it just some bizarre problem I'm making? No, it's not. They're there for a reason. You'll oftentimes see a log of an absolute value, but why was that? What's the domain of the natural log function? All positive, right? And so you can't input a negative number into a natural log function. And so how do we prevent inputting a negative? Well, you put in an absolute value place, right? And so do they do anything? Not really. They're just there to protect the domain, so you don't, so you're only inputting positive values. And so the point I just wanted to make with this, I want to remind you about something important. You tell me, what's the answer to this? This is one of our derivatives you gotta know. What's the derivative with respect of the natural log of u?
U prime over U.
Good, u prime over u. So now, answer me this. What is the derivative with respect to x of the natural log of the absolute value of u?
The absolute value.
It's u prime over u, that's all it is. You don't have to do anything. The absolute values, you can just effectively ignore them. They're just there because of the domain of the natural log function. Right? So this is pretty easy, right? It's just a derivative of sine over sine. Okay? So what would we get?
Cosine over sine.
What is that?
10.
Okay? Makes sense? Okay, this one, why is this one up here? What's the,
You can use your log rules, so you're dividing logs.
Right.
You're subtracting.
we'll take advantage of those properties of logs, right? What do logs do? They're gonna step everything down on that order of operations tree, so quotients become something easier. Quotients just become differences, right? So I could rewrite this as, I'm just gonna do some work inside the brackets here. What am I taking the derivative of? Well, the log of x plus 3 divided by x minus 3, the log of a quotient equals the difference of the logs, right? So I could write that as what? When you say ln, what do you really mean?
Natural
You meant to say natural log, didn't you? That's what I thought. Okay, so now those are both pretty easy ones, right? Now we can just differentiate that term by term. I'm just gonna get two terms in my answer. Well, what would the answer be? Might as well just write it. Yeah, what's the derivative of x plus 3? 1 minus, there it is, right? Much easier that way though, right? If I didn't do it that way, this would be kind of a tricky, you could make a mistake, there's a lot to do. I'd have to do the derivative of this would be a quotient rule, right? I gotta do the whole quotient rule divided by that quotient, and then I'd have to flip and multiply. It's a lot of extra work. So once again, you see that really most of calculus is not about getting the right answer. Well, it is, but it's about how do you do it, right? Are you strategic about how you do it? Okay, this is one I thought, you tell me if you want, we did a ton of these, but it's been a little while. This is one where when we do this derivative, we're gonna have to use that process to simplify it of factoring out the least common power, right? So let's set it up and then you guys tell me if you wanna finish. So I would use maybe, how would you probably rewrite this? You could use the quotient rule.
Just
Do
apply it.
3t.
Right, we could make it a product rule, right? That probably be, product rule is a little easier than the quotient rule. So we could write this as t squared plus 6 times,
3t minus 2 is -5.
good, and now if I do my derivative, I'm gonna get what? First one times,
Negative 5.
okay, good, -5,
3t minus 2, -6.
good, to the -6 times plus that.
Times 2t.
Times 2t, good. Okay, so we'll finish it. Okay. So what are we gonna do then? We can take the first, let's go ahead and maybe clean this up just a little bit. So I could combine those two, right? And get a -15 t squared plus 6. That was really tricky. Rarely do I think ahead like this, but I'll do it today. So, times okay, everybody agree that's my first term? I just split it up. Plus 2 times t. This I don't really need. I didn't really need that others, did I? Times 3t minus 2 to the -5. Okay, so what is my only common base here?
3t.
3t minus 6, or minus 2 in this case, right?
Yes.
So that's the one thing I can factor out of both terms. And what do I get if I factor out, and there's no common factor, no numerical common factor. So if I factor out that base, well, first of all, what power of that base can I factor out?
Negative 6.
Good, it's because it's got to be the least common factor, the smaller of the two, right? -6 is a smaller power than -5. So I can take out a -6. Now, what's that going to leave me with from my first term?
Negative 15.
Okay, good, I've got my -15.
Times t squared is 6.
I've got my t squared plus 6, and that one's completely factors away, right? Okay, plus, I've got my 2t, and how many of those are there? One. Good. Right, I'm left with 3t minus 2 to the -5 divided by 3t minus 2 to the -6. Hand to the -5 divided by hand to the -6 is hand to the -5 plus 6. Right, and that's always gonna work, isn't it? I'm always gonna have a difference of 1 there because of the power rule. That's why those are different by 1. So there's my answer. All I've got to do now is write it as a fraction. So that goes to the bottom. And then I could distribute the -15 through, distribute the 2t through, and combine like terms, that'd be done, right? Okay, I won't even finish it so we can get through everything. Okay, do you want to look at one of these?
Sure.
Something like that?
Yeah.
Where?
Yeah.
Okay, so we want to know, where does this function, so it's a trig function, have a horizontal tangent line? Okay. Well, first of all, what's significant about a horizontal tangent line? What's going to be interesting about a horizontal tangent line? Slope is 0. Good, so that's where the slope is 0. So I want to, slope means derivative, right? So we'll take the derivative. What is the derivative of that?
2 this
Okay, and I want to know where is f prime equal to 0. So that just gives me, well, we'll find out. Okay, so I gotta solve a little trig equation. To solve a trig equation, what am I gonna do?
Move to the side.
Okay, I might move forward to the other
Yeah.
side. So I get 4 cosine x equals 2. Now what? Divide by 4. Cosine x equals 1/2. So that's smart. We wanna isolate the trig function, and then it's a unit circle issue, right? So where does cosine x equal 1/2? Well, we just go to our unit circle and find out. Cosine is the x or y coordinate on unit circle. X coordinate. So we wanna know, there's 1/2, so I wanna know where on the unit circle is x equal to 1/2. Well, it's gonna be at that point right there where the coordinates are 1/2 what?
High up.
Not that we care, but what would the coordinates be at that point? If x is 1/2, what would y have to be? Square root of, there you go. Square root of 3/2, right? And down here, if x equals 1/2, what does y equal?
Negative.
Negative square root of 3/2. We didn't really care, I wanted you to think about the unit circle a little bit. What we care about are the angles, right? So what is this angle here?
It's
Right? I mean, I know we don't use it every day, so it kind of goes away a little bit, but that's the pi/3 angle, isn't it? If you think about all the important angles in quadrant 1, there's the pi/6, pi/4, and pi/3, right? And that's gonna be the biggest one, okay? So that's a pi/3. What's this one down here? We could just call it negative pi/3. Yeah, we would just go backwards pi/3. Okay, so then if we want to find all of the places for what values of x, where does that happen? There's an infinite number of revolutions around the unit circle there, right?
yeah.
So I could say pi/3 plus
2k pi.
2k pi. If k is just any integer, then I'm going to take some integer number of laps, positive or negative, around the unit circle to get to that spot. So I'm going to get 2 solutions. One is going to be x equals pi/3 plus 2k pi, and the other one, that one orange, is going to be x equals negative pi/3 plus 2k pi. That's it, right? Questions on that? Super easy one. This isn't even calculus, but I want you to remind yourselves what average rate of growth means instead of instantaneous. So if I want to, and there's a graph that goes with this, but you don't even need a graph. Compute the average rate of growth of the city population from 1970 to 1980. What is that? Average rate of growth. Change in y over change in x, right? It would be the slope of the secant line on the graph. So all that's going to be, the average rate of growth, is just going to be, the change in y is going to be from 1970 to 1980, so it's going to be, this one's going to be 191,246 minus 112,568 divided by 10. And that should give you that amount. I can plug that in. If I want to calculate from 1990 to 2000, I would just use those values, right? So an average rate of change is not calculus. That's just slope of the line connecting the 2 points on the graph, or change in y or change in x. Yep.
The price balance is like just the graph and overestimate, underestimate.
Yeah. I'm not going to put that on the test.
Oh, okay.
Yeah.
Okay.
But I mean, it's not that it's not a good question, but all you'd have to do there, so here, if we have time, I'll go back and put the graph up. I want to make sure I get through this last couple of them. Okay, so what about this one? We talked a lot about this one. You tell me, we can at least talk about how to do this, right? So they're giving us the position function is right here. S is equal to f of t, right? So I could calculate velocity and acceleration pretty easily, right? So velocity we could calculate, if this is s of t, What's v of t?
3t squared
I'm just gonna differentiate, right? Three t
minus
squared
24t plus 45.
plus 45. What's the acceleration?
6t minus 20.
Okay, that's all we need to do all this stuff, right? It says graph the, well, you don't have to graph the position function, so probably gotta tweak this question just a little bit for the test, so I'll take that out. And I would even be willing to, maybe, let me think about it, I might even be willing to like let you use it, graphing utility, just to get answers more quickly on this one.
Yeah.
Okay, so I might embed a graphing utility for this question.
That would be used.
Okay. But if we wanted to know when is the object stationary, well, where would that be?
0. No.
When, so, now let's get at how do we apply this stuff to find out when is the object stationary?
It
Well,
would be
what's happening when it's stationary?
The velocity is 0.
Velocity is 0, right? So I'm just gonna set the velocity function equal to 0 and solve. I'll give you a graphing utility to do that one. So you can just graph the function and find the x-intercepts on the graph, right? Okay, make it easier. I just want you to know how to do it. Determine the velocity and acceleration of the object at t equals 1. Well, what am I doing there? Plugging in 1, right? No big deal. Okay, you know how to do that on Desmos, right?
Yeah.
There's a really easy way to do it. On Desmos, even on the scientific, you can do this. I can literally just type, I can define the function in one row on Desmos. So I would type in v of t, exactly that, v of t equals blah, blah, blah. Go down to the next line and do v of 1, and it'll tell me what the output is on either the scientific or the graphic. That's a pretty cool feature, right? Determine the acceleration of the object when its velocity is 0. Well, a of 0, no big deal. And then what about the last one? On what intervals is the speed increasing? This is probably the tricky one. Where would speed be increasing? Speed is a scalar, right? Speed doesn't, it could be going in the positive or negative direction and having the speed
What
increase.
is the
Speed would
velocity?
increase.
Not
Right,
velocity.
right after velocity.
Okay, but there's something,
What acceleration stops?
well, it has to do with the relationship between the acceleration and the velocity. And this is, once again, this isn't really calculus, but it's an important application, I think, of calculus. So, once again, let's look at our kinematics on a line up here, right? That's the positive direction, that's the negative direction. So this is positive velocity, this is negative velocity, right? Think invisible, I know the invisible hand seems dorky, but it really is helpful. If I'm increasing my speed in that direction, the invisible hand is pushing me in which direction? Positive. So that's
Yeah.
positive acceleration, which makes sense, doesn't it? Right? Okay, what if I'm slowing down in that direction? In the positive direction. The invisible hand is pushing me in the negative direction, and so that's negative acceleration, right? If I'm slowing down in the negative direction, the invisible hand is pushing me in the positive direction, and so that's positive acceleration, right? Okay, so then think, what are the only circumstances where my speed could be increasing? If I'm increasing my speed, right, which is just the magnitude of my velocity, how fast I'm walking, regardless of direction, in that direction, in the negative direction, what has to be true about the acceleration and the velocity then?
Has to be negative.
They'd both have to be negative, wouldn't they?
Yeah.
Right? So I'm moving in the negative direction while the invisible hand pushes me in the negative direction. Agreed? If I'm moving in the positive direction and the invisible hand is pushing me in the negative direction, I'm slowing down, right? Okay? If I'm moving in the positive direction, then the invisible hand would have to be pushing me in the positive direction for me to be speeding up, right? So what we're really getting at in that last one is the speed only increases when the acceleration and the velocity have the same signs. And they're either both positive or both negative, right?
Yeah.
Okay? That's a little tricky one. That's a pretty good question. And that's it. Yeah. Make sense? Okay?